Right. So this week we're going to be looking at how we can answer what I think would be a fairly common question, right? Given 2 points that exist on a raster, how can we figure out the best path to go from one point to the next, given a series of variables that would pose constraints on it? And so for this example that we're going to walk through the steps for, right, we have these 2 points and then we have elevation, distance from roads, and precipitation. And the idea is that these other variables here would pose some sort of hindrance or, as we'll use the terminology in a minute here, cost to being able to go from one cell to another. So what we're actually going to be doing is creating a path over a raster, or sometimes called a path over a surface. And the way that we're going to approach this is to break it up into 5 steps, with the 6th step being make sure you have everything you need. So for the data gathering portion. So what we're going to do is we're going to start by figuring out, given the 2 points that we have, which one we're going to start at and which one we're going to stop at. Then we're going to convert all of those raw data layers, so in our case the distance to roads, elevation, and precipitation, into what's called a cost surface. And this cost surface is going to look very, very similar to how we did the weighted overlay suitability. Just the interpretation of what the values means is going to be slightly different. Then we're going to convert that cost surface to what's called a cost distance surface, which is going to take into account the fact that we're trying to travel, so we need to incorporate some form of distance into that. Once we've got the cost surface distance, we will convert that into what's called a directional surface, which is basically just going to tell us from any one cell what direction we should go next to minimize cost. And then finally, to actually create the path, we start at the endpoint and then work back across that directional surface to figure out how to get to the beginning. So what we're going to do in this video is go through each of these steps on a fictitious data set, really hammering home the sort of fine scale detail of how this works. So let's start with step 1, right? We've got our data, so we're starting with step 1. We have 2 points. We need to figure out which one we're going to call our start point and which one we're going to call our end point. For the sake of this example, the leftmost point here is going to be our start point, and the rightmost point here is going to be our stop point. Okay, so check. We've specified our start point, we've specified our end point. That's pretty easy. Next, we need to convert everything to a cost surface. And like I said before, this is going to look very similar to the weighted overlay. And in fact, it has the same steps as weighted overlay, where we're going to reclassify to a common scale, assign weights to each layer, and then calculate a weighted sum for that system. So this is where things are different from suitability. So when we talked about weighted overlays and suitability, we talked about that suitability scale. We're applying the exact same concept here, except instead of a suitability scale, we have a cost scale. And so you can see what I've done here is I've set up 3 different reclassifications to the same scale, 1, 2, and 3. And I picked 3 here just because it keeps the interpretation relatively straightforward, right? Low cost, medium cost, high cost. And the key difference here between weighted overlay for suitability and the cost surface layer is that with suitability, right, these higher values were a good thing, right? They meant that that particular value range was desirable for whatever we were trying to model suitability for. For a cost, it's the opposite, right? A high value here means that this is a high cost, meaning that we are going to be more likely to avoid these values here, right? So it's almost flipped from the idea of the weighted overlay, right? Again, low cost means means that we're more likely to use it. High cost means we're more likely to avoid that cell when we're creating our path. So just like with the weighted overlay, what we're going to do is we're going to take in these cost scales and apply a reclassification. So for example, this value of 1.5 gets fed into this reclassification, right? It fits between 1.2 and 1.5. Therefore, the output is going to be a cost value of 3, right? For this pixel here, right, same concept, right? We feed it into the reclassification. Its value is between 0.75 and 0.94. Therefore, it's going to have a cost value of 1 in the final output. Right, and again, precipitation works the exact same way, right? We can pick this right here, right? The input value is 8. The reclassification to cost scale, 0 to 9. So 8 would end up having a cost value of 1, right? So 8 falls in that range, becomes a 1. Right, this is the same concept, again, as weighted overlay, except that we flipped the interpretation. Lower values are going to be more favorable. Higher values are going to be less favorable in terms of the cost. Okay. So once we've assigned weights to each layer, or once we've classified each data set to a common scale, the next step is going to be to assign weights to each layer. Right, and so you can think of the weights as how important that variable is to the overall calculation of cost. Right, again, very similar to suitability. And so what I've done is I've assumed that since we're going to be traveling, we want to be close to roads. That's going to make traveling easier. Right, going uphill is going to make things a little harder. And we don't care too much about precipitation, so I've picked, weights accordingly, right? 0.5 means that half of our overall cost is going to be weighted to how far away we are from a road. 35% is going to be weighted to elevation, which again, right, higher elevation values mean higher cost, meaning we're more likely to avoid those cells. So once we've figured out the weights, we then have to calculate what's called a weighted sum. And again, going back to the idea of suitability, right? The weighted sum for each pixel is going to apply this general equation, right? We're going to take the value times the weight for the first variable, the value times the weight for the second variable, and the value times the weight for the third variable. And then we're going to apply this to each and every pixel in the data set. Right, so going through an example here, right, so if we take these 3 variables, we apply the weights we came up with last time, right, this is our output for our weighted overlay. And what I've done is, you can see for the red, is I've actually pulled that equation out just to kind of walk through as an example, right? So calculating the red cell here, right, our elevation is 2. The weight for elevation is 0.35, so that's where this 0.35 comes from, right? Distance from roads, the value is 1, that's where this 1 comes from, times 0.5, that's the weight, and then we add the precipitation value is 3, times the weight is 0.15. If we do the math on that, right, we get 1.65 going here, right? So I also did the yellow just to contrast, even though we have the same numbers, right? In this case, it was 2, 1, 3. In this case, it's 2, 3, 1. So we have the same numbers, but they're in a different order. And this is going to highlight the importance of the weights and the fact that the weights can actually drastically change the overall cost value. Right, so in this case, right, this 2, again, is coming from elevation times 0.35 for the weight. In this case, right here, we have a distance from roads of 3 times 0.5. So this is a 3 as opposed to the previous example as a 1. And then precipitation in inches, right? Again, it's that 1 times 0.15. If we do the math on that, right, we get 2.35. And what I want you to realize is even though we had the same cost values, right, 2, 1, 3, 2, 3, 1, by changing the order, right, we applied the weights to different values, right? In this case, right, the 0.5 weight is being applied to 3, as opposed to here, the 0.5 weight is being applied to 1. And because the order matters here, right, we end up with a much larger cost value associated with this cell than this cell. And that's because the distance from roads was much higher and the weight for that was much higher. So the overall cost went up, even though we were using the same numbers just in a different order. So order matters is what I'm trying to get at. Right. So once we convert from a cost surface, the next step is going to be to calculate the distance surface. So in general, we'll talk about the equation in a minute. What we're going to be doing is multiplying the average costs of two neighboring cells. So this cell and this cell, for example, we're going to be multiplying the average cost from our cost surface by the distance between these two cells. But it's important here to understand what we mean when we say distance, right? How do we actually measure distance? So there's 3 cases. The first case is that the cells are either horizontally adjacent or vertically adjacent, right? And in both cases, what we're actually measuring is the distance from the center of one cell to the center of the next cell, right? From the center of one cell to the center of the next cell. And in the case of horizontally arranged and vertically arranged neighbors, this distance is just the cell size, right? Just take a second, think that through about how that makes sense, right? That this to the edge is half of the cell size. This to this edge is half of the cell size. Therefore, from here to here is going to be the cell size. Okay, so if your pixels are next to each other horizontally or next to each other vertically, all we have to do for distance is just take the cell size. Right? But there's another type of adjacency, and that occurs when we have cells that are diagonally adjacent. Okay, right. Now we're still going to measure from the center to the center, but right, we're no longer dealing with horizontal or vertical, so we can't just use the cell size outright. Instead, what we have to do is think for a second about what this distance would actually be. And what we can do is we can think of this in terms of a right triangle, right, where we have the cell center of one over 90 degrees to the cell center of the other. The distance would be this hypotenuse here. And because of the fact that we are assuming that all cell sizes are the same for all of the data that we're using, we can actually abstract away the concept of cell size for a second and look at just a unit triangle. That's where each side is 1, right? Because this is going to work as long as our cell sizes are the same for all of the cells, right? Whatever we find with this sort of unit triangle, we can apply as a scale factor to the distance here for any cells ever, right? So once you understand this relationship here, you'll understand the scaling factor for all data sets forever. So, right, if we have a side length of 1 and a side length of 1, using the Pythagorean theorem, right, 1 squared plus 1 squared, well, 1 squared plus 1 squared is the square root of 2. Square root of 2 is approximately 1.41. Right? Therefore, when you have diagonal cells, whatever the cell size is, if you multiply it by 1.41, you're going to get the distance between two diagonal cells. Okay? So just to recap, if they're vertical or horizontal, we just take the cell size directly as our measurement of distance. If they're diagonal, then we have to apply this 1.41 scaling factor that comes from this unit triangle Pythagorean theorem, that this diagonal would be root 2. Okay? So now that we know how to measure the distance between cells, what we have to do then is begin to incorporate into this the actual costs. And the way that we do that is with this sort of general equation. And this general equation has two pieces. It has the to and the from. So the to is going to be the cell you're traveling into. The from is going to be the cell you're traveling from. Right? So if we were to go from this cell to this cell, right, this cell would be our from cell, this cell would be our to cell. And what we're bringing in is the distance that we just talked about relative to some portion of the cell size, the cost to and the cost from. This is coming from our cost surface that we calculated using that weighted overlay. And you can see here we're just basically taking the average cost between the two cells. And then as we begin to move out away from the beginning, we're going to accumulate cost from all of the previous cells. Right? So you can think of the cost of any individual cell as the total cumulative cost that it would take to get from the start to that cell. Right? So this equation is going to be applied to every cell relative to every neighboring cell, starting from the start point and radiating outward to the end of the data set. Okay? So let's go ahead and look at some examples of how this calculation works. Right? So this, again, just to keep track, this is the general equation from before. I've brought back in our specific start point here. So this is where we start from. This is a start point we defined. This is the cost surface that we calculated from step 2. And what we're going to do is we're going to combine these things together to generate our output over here. We're going to start filling in our cost distance surface. So by definition, the start point has a cost distance of 0, right? Because we're not traveling anywhere. So it has a 0. So what I've done is I've started at the beginning here at our start point, and I've calculated outward, right, the cost distance of all of the neighboring cells. And I want to look at 3 examples. One going horizontally, one going horizontally, one going vertically, and one going diagonally, just so that we can verify that we understand where all these pieces are coming from. And keep in mind, the cell size, we're going to call 30 meters. Okay? So let's go ahead and work horizontally first. So we're going to go from this cell to this cell. So this is our from, this is our to. So the equation for the distance, the cost distance, right, is going to be distance, that's 30, that's coming from the cell size, times 1.35 plus 1.15. Well, that's coming from our cost surface here, right? 1.15 was the cost of this cell here. 1.35 was the cost of the to cell here, right? And so 2 plus from divided by 2 gives us the average. And then we're adding to that, right, the cost of the from cell. Well, in this case, by definition, right, our from cell doesn't have any cost, so we're adding 0 there. So if we do the math on that, what we get is 30.75. Okay, so the cost of going from this cell to this cell is 30.75. What if instead of going to the right, we went down? What's the cost of going from this cell to this cell? Well, we can apply the exact same equation, right? We have our distance, which again, for vertical arrangements, we just use the cell size, so that's 30, times, right, the cost to and the cost from. Well, in this case, right, this is our cost from, it hasn't changed. Our cost to is 1.3, right? So this 1.3 is coming from this 1.3 here. Again, we're taking the average, and then we're adding the cost from. Well, again, right, by default, this pixel, this cell, doesn't have a cost, so we're adding 0 there. So if we do that, what we get is 36.75. Right, the cost of going from this cell to this cell is 36.75, and I rounded it to 36.8. Okay. What about going diagonally? Right, so we went right, we went down. What about going diagonally? Well, the equation is going to look very, very similar, right? It's still distance times the average cost plus the DC. But in this case, right, our distance is this 30 coming from the cell size of the raster times, right, this 1.41. This is again coming from that distance scale because we're going at a diagonal, right? This is the square root of 2 factor that we talked about previously. And again, right, there's no cost from because this is defined as 0. So the cost of going diagonally, right, is 63.45. So you can see here that simply by virtue of the distance between these 2 points being on diagonal instead of straight, right, we've increased the cost considerably because there's more distance we have to travel. It costs us more distance to go from the center of here to the center of here than it does from here to here. So that's reflected in the fact that our cost distance surface has a higher value. Okay, so that's how we would evaluate going to any of the neighboring cells. What about 2 out? What if we wanted to go from this cell to this cell? What is the cost going to be here? Well, there's really three ways we could do it. Well, there's a lot of ways we could do it, but there are three that make the most sense, right? We can go to the right and then to the right again. We can go up diagonally and down diagonally, or we can go down diagonally and up diagonally, right? And so we end up with three potential options to go from the start to the target. Which one do we pick? Well, let's start by figuring out what the cost surface would be for each of these paths, right? And so we can simplify this to be going down diagonally, so from this cell to this cell, going right from this cell to this cell, or going up diagonally from this cell to this cell. Let's see what that looks like mathematically, right? So going from this cell to this cell, what we're doing is we're doing the exact same calculation we did before, right? We're including that diagonal factor here, right? We're pulling in the cost of both of these cells. So 1.85 for this cell, right? 2 for this cell, right? Because this cell's value is 2 here. Taking the average of that. It's just like what we did before. But now, right, we're having to pull in that accumulated cost, right? That's 63.5, because we're assuming that, oh, there's a cost associated from taking this path, right? This is the sort of accumulated cost of everything we've done so far, right? So to go from here to here would have a cost of 144.9. What about just going right? Going right and then right again? Well, that would have a cost, right? Because we're going horizontally, our distance is still just regular 30, right? We don't have to apply that scaling factor. The to cost is the same, right? Because we're ending up in the same cell. The from cost, right? Now we're going to pull the from value from this cell is this 1.35. So 1.35, taking the average again. But now, right, we're pulling in the cost of this cell here of 37.5, right? So going right and then going right again has an overall cost of 87.5. Right? And then we have the option of going down and then going up. So to go from this cell to this cell, right, we're going to calculate, again, it's going to look much like the first option. We have the distance with that weight factor, plus, in this case, right, we're going from a cost of 2 to a cost of 2. So it's 2 plus 2, taking the average. The cost of this cell we calculated out previously to be 74. So again, right, we're pulling over the accumulated cost of all of the other moves we've done so far. If we do this math, right, 158.6. So let's take a step back. We have 3 valid routes, each taking the same number of cells to get to the target. Which one do we pick? Because we can only assign one value to this cell, right? This 2 cell can only have one distance cost value. Generally speaking, unless you have a reason to do otherwise, you always take the lowest value, right? And so in this case, 87.5 becomes our cost value, right? Because this is the lowest option. So even though we had multiple different ways we can get there, unless you have a reason not to, you always take the lowest value possible. Right, so you can see here we've added 87 point, in this case I rounded it, 87.8 to our cost distance. Right. And so if you want to fully understand this, this would be a good time to pause, ponder, maybe go through, work out a couple more, maybe try and work out what you would calculate for this pixel here based on all the different options you could take. But if you do that, what you end up with is this finalized distance cost raster, right? So this distance cost raster here, each cell represents the total cumulative cost to get from the origin to that cell, taking the most efficient route along the way. Okay? So again, right, each cell value here represents the total cumulative cost to get from the origin, right, from the start point we defined, along some combination of cells to this cell in the most efficient way possible. Okay? So we have our cost distance surface calculated. Now we have to take that and convert it to the direction surface. Okay? So this is a little bit strange in the sense that if you've never done anything like this before, it can be a little bit confusing as to how we're assigning values. But what we're going to do is we're going to take any cell, we're going to look at its neighboring cells, so the neighboring 8 cells that are around it. We're going to figure out which cell has the lowest value. And then we're going to assign to our cell that we're looking from a coded value with which direction we would have to go to enter that cell. Okay? We're going to go through several examples because this is, I think, a little bit confusing. But basically what we're going to do is from the cell we're standing on, if we have to go right to enter the lowest value cell, our cell would get a value of 1, right? If from our cell we had to go northwest to enter the lowest cell, our cell would get a value of 6, right? If from our cell we had to go southwest to get to the lowest cell, our cell would get a value of 4, right? So this 9-cell template here, this is the coded values and what they mean, right? So if our cell has a value of 1, that means the lowest value would be to the right. So we would go from our cell to the right. Take a second, think about this. We're going to go through several examples of how this works so that you can get a good feeling for it. Okay? So let's look at this example here. So we're going to start at our, in this case, we're going to start at the point of our origin. This is our start point. So I've cut out its neighbors. So this is the point we're looking at, and these are its neighbors. So what we're going to do is we're going to, based on this cell, figure out what direction we would have to go to the lowest possible cell value neighbor, and then assign to our cell the direction based on this coded value options here. Okay? So, right, if we are here, right, our lowest possible valued neighbor exists down, right? This 37 here, this is our lowest possible neighbor, right? Of all of the neighboring options that we have, this is our lowest neighbor. We get to our lowest neighbor by going straight down. Therefore, right, in our output, we would have a value of 3, right? This 3 is saying, hey, from this cell, to get to our lowest neighbor, we need to go down, right? Because again, this was our starting point of the neighbor options we had. Our lowest value was down. Therefore, we assign to us the coded value that means go down, which is 3. Okay, let's look at another example. If instead of starting here, let's say we were looking at the pixel 1 and to the right. So we're looking at this pixel, the star. This is our target pixel here. So we're going to look at all of our neighbors. Right, so this is all of our neighbors. So, right, in this particular case, right, we have our lowest possible neighbor value is here, right, because our starting point was defined to have a cost distance value of 0, right? Our lowest possible pixel value, our lowest possible neighbor value is 0. So to get from here to here, we had to go down and to the right. Or sorry, down and to the left. Down and to the left, right? If we look at our coded value options, right, down and to the left has a coded value option of 4, meaning the value in the output for the pixel we were standing on is going to be 4. Because this 4 means, hey, from here, go down and to the left. Okay? Let's do one more example because I really want to make sure that we understand where these things are coming from. Right, so starting with this pixel here, looking at its neighbors, right? So these are the neighbors that it has. So starting from here, what direction do we have to go to get to our lowest possible cost distance value neighbor? Well, of these options, right, the lowest is 88. To get to 88, right, we have to go to the left. Right, we have to go from here to the left. Our options are to go from here to the left, a value of 5. So our pixel, the one we started in, is going to get a value of 5 because 5 says, hey, if you start here, go to the left. Okay? So once we calculate the surface direction or direction surface for all of our cells, we end up with something that looks like this. Okay? So if you are feeling confused about the direction surface, I encourage you to pause the video now and work through a couple more to figure out if you can get these values to match up based on our coded value matrix that we have here. Okay? So once you have the direction surface, what we have to do next is work backwards from the endpoint to the start point. Right, so we calculated the cost from the start point outward. We converted that cost surface to a direction surface. Now we're going to take that direction surface and we're going to trace backwards from the start point, or from the endpoint to the start point, right? And so we're going to bring in that direction matrix that we use to create the distance surface to help us interpret where we go from a given cell. Okay? So we're going to bring in our endpoint, which again, for reference, right, we ended at the top corner here. So this is where we're going to start because we're tracing backwards. So where do we go? Well, we look at the value, right? Because this is our direction surface now, right? Our direction surface has a value of 4. What does a value of 4 mean? Well, a value of 4 means if you start here, a value of 4 means we have to go down and to the left, right? And so that's exactly what we will do. We will go down and to the left, right? So that puts us, now we're here. So where do we go from here? Well, we're going to do the exact same thing we just did, right? We're going to take this value, we're going to read it through our little matrix here, right? A value of 4, again, in this case, means down and to the left, right? So that's exactly what we're going to do. We're going to go down and to the left. So now we get to this cell, and we have to figure out where do we go from here. So again, right, we're going to take this value, we're going to put it into our direction matrix here. A value of 5 means to go left, right? So we're going to go from here, we're going to go left. That gets us here. In this basic example, here is actually where we stop, right? We've reached our goal. So what we would do in this case is, now that we've reached our goal, right, we would have a raster showing us the path from our endpoint to our starting point. And we could take that and we could convert it to vector and display it however we wanted to. Right? So just to sort of recap what we did, right, we started with a set of raw data and 2 points in space. We defined one point as the start and the other as the end. We then converted the raw data from raw form through a cost scale to a cost surface using the same concepts of weighted overlay, where we did a reclassification to a common scale, assigned weights to each of the layers, and then did a weighted sum to get the cost surface. We took the cost surface and the distance between cells to calculate a cost distance surface radiating out from the origin. We took that cost distance surface and we converted it to a direction surface using this directional guide to determine which way to go. And then finally, we worked backwards, starting from the endpoint, using the directions to determine which way to go to create a path to meet the start point. Okay. So at this point, do you have any questions?